Good morning, good evening, good afternoon, and welcome back to another math lesson. Today we're going to be starting off our new unit on transformations of functions, starting with lesson number 1, translating graphs of functions. So let's get started. We're going to sketch the following basic pairing functions, okay? So we're going to go through the different functions, right, that we will be transforming, basically picking up and moving around, stretching and compressing, okay, throughout this unit. Okay, so it's best that we know what the original graphs look like, okay? So the first one we have is y is equal to x. That is a linear graph, okay? And it looks something like this. Okay, so now that we have this graph, we can now just state the domain. Well, the domain is going to be negative infinity to infinity. Okay, make sure you include it in round brackets if you're going to write your domain in range like this. Okay, or we can state it as x is an element of all real numbers. Okay, so there are no restrictions on this graph. Okay, the range is very similar. It is negative infinity to infinity, as there are no restrictions in the y values, or we can say that y is an element of the real numbers. Okay, we can say that the x-intercept is going to be at 0, so x is equal to 0 in this case. And we can say for the y-intercept, y is equal to 0. You've done many graphs like these already, probably in grade 9 and grade 10. Okay, so this is just a quick little review of what this linear function just looks like. Moving on, we have the next function, which is y is equal to 1 over x. Okay, this is called a reciprocal function. Okay, so this is called a reciprocal function. Okay, so what happens is we actually have a vertical asymptote, okay, at x is equal to 0, because we don't want our denominator to be 0, right? We can't have our denominator being 0 or else it doesn't exist. Okay, so we're going to have a vertical asymptote at x is equal to 0. And we're also going to have a horizontal asymptote at y is equal to 0. Okay, so our graph is going to look something like this. You will have points here and here. And it's going to follow along the asymptote like this, touch this point and carry on. And it's going to do the same thing in this quadrant. It's going to follow along the asymptote, hit this point, and then follow along the other asymptote. Okay, so this is what the reciprocal function graph looks like. Its domain is everything. So x is element of the reals, except x cannot be 0. Okay, so x can be anything but 0. The range is very similar. Y is an element of all real numbers, except y cannot be 0. Okay, so it'll never reach those asymptote points. Our x-intercept and y-intercept, because the asymptotes are at x is equal to 0 and y is equal to 0, where it crosses both axes, we don't have any. So there are no asymptotes, or none. Okay, so that is what. Moving on, we have y is equal to the root of x. Okay, so this is a square root graph. So a square root, or what's also called a radical graph. Okay, so again, all you're going to do is you're going to take the square root of all your functions. So it kind of looks like a quadratic function. Okay, but you're just going to take the square root of all your y values. Okay, so it is going to look something like this. So that is what a radical graph will look like. So our domain is going to be x such that x is going to be greater than or equal to 0, provided that x is an element of all real numbers. Okay. Also, or you can write it as 0 to infinity. We're going to include 0, but not include infinity. Range, okay, is going to be actually the exact same. So it's going to be y such that y is greater than or equal to 0, provided that y is an element of all real numbers. Okay, and same idea, or it could be stated as 0 to infinity for our y values. Okay, make sure that we are including 0 in this case, so it's going to be a square bracket by the 0, but we are not including infinity because it'll never reach there. Okay, and then for the other way we wrote the domain and range, this is how it's stated. It's x, and then this little line says such that. Okay, x such that x is great. All x values are greater than or equal to 0, and this little comma is provided that. Okay, provided that X is an element of all real numbers. So this is all real numbers. All real numbers. Okay. That's basically what's stated. Okay, so that's how it's spoken. Like that's how that's spoken. That's how it's said. Okay. Our x-intercept is going to be at x is equal to 0, and our y-intercept is going to be at y is equal to 0. Okay. For your domain and range, either way is correct in which you write it. Moving on with some domain and ranges that I will write, I will try to write it in both ways. But don't be alarmed if you just see it written in the in just one way. Okay. But that is how a radical graph is made. Moving on, we have y is equal to x squared. So that is our quadratic graph. Okay, so that is our quadratic graph. And you've done many of these in grade 11. Okay, so the graph is going to look like this. Now that the graph is finished, we can safely say that the domain is all real numbers. Okay, there is no restriction on the domain. The range, however, so the range is going to be y such that y is greater than or equal to 0, provided that y is an element of all real numbers. Or it can be from 0 to infinity. So we're not including any negative values for this quadratic function. Okay, that's for the original quadratic function. Okay, the x-intercept, okay, that's where it crosses the x-axis, and it does that at 0. And for the y-intercept, that's where it crosses the y-axis, and that's done at y is equal to 0. Okay, so again, this is a nice little refresher of the quadratic graph. Moving on, we have y is equal to 1 over x squared. Okay, so the nickname that we give this function is called an inverted funnel. Okay, and how this looks, it's going to look very similar to the reciprocal graph. Okay, except the part that's below the x-axis is actually going to be up in the positive part. So all your y values are going to be positive in this case. So, okay, what do I mean by that? Well, I mean that we're going to draw out the asymptotes the same. So like I said, it's very similar, the inverted funnel. Okay, where it has your x asymptote being at 0 and your y asymptote being at 0 as well. So your horizontal and vertical asymptotes are still in the same spot. Okay, your graph looks very similar as well. So you still have this part here. So this is similar. I'm going to redraw that. So this is going to be similar here. Okay, so it's going to touch this point and carry on. Now, the next part, so the reciprocal part, okay, and the reciprocal graph would be down in the lower half, okay, of the graph. But now it's going to be flipped up because we have this squared. All the negative y values will actually become positive. So it's going to be here. So it's going to look very much the same. It's going to come down, touch this point, and carry on. Okay, but that is essentially what the inverted funnel looks like, okay? The domain is going to be everything for your x values, provided that x cannot be 0. Okay, so it's the same thing as your reciprocal graph. The range, well, the range has to be greater than 0, provided that y is an element of all real numbers. Okay, so the range has to be everything bigger than 0. Okay, so that means that it's basically 0 to infinity, not including 0 or infinity. Okay, your x-intercept, okay, that's where it crosses the x-axis. Since it doesn't, there are none, and the same can be said for the y-intercept. Okay, so again, very similar to the reciprocal graph. Okay, but in this case, your bottom half of the reciprocal graph is actually flipped up into the positive part, okay, for your y values, okay? But that is what an inverted funnel graph looks like. Okay, moving on to the next graph, we have y is equal to x to the power of 3. So the name of that is going to be a cubic function, okay? And essentially how it's going to look, like this. So we have points at 0, 0, 1, and 1, and then 2 to the power of 3 is going to be 8. Okay, and negative 2 to the power of 3, okay, is going to be negative 8. Okay, also negative 1 to the power of 3 is negative 1. Okay, so it's going to look like this, and it's going to have this kind of shape. Okay, so it's going to come down. and carry on. Okay, so this is what a cubic function looks like. I'll just re-put the dots here so you can see it. Okay, its domain for your x's is everything. Okay, there are no restrictions on your x's and there are no restrictions on your y's. Okay, your x's and y's can be anything. Your x and y intercept, well, those will both be at 0. Okay, that's where it crosses the x and y axis. Okay, but this is essentially what a cubic function looks like. If you need to draw out the table of values, I suggest you do so. So you have your x and y, right? Do -2, -1, 0, 1, 2. Right? Start off with those values, and you should get -8, -1, 0, 1, 8. Okay? And that's where I plotted those points. Okay? But that is essentially what a cubic function looks like. Okay? And again, what we're going to do is we're going to pick up and move these parent functions around. So that's why, again, these are what the original graphs look like. Okay? But to sum up, this is what the cubic function will look like. Okay, moving on to the last one, we have the y is equal to the absolute value of x. So this is going to be an absolute value function. Okay? Okay, so essentially what an absolute value function is that it sets all of its y values positive. So there will be no negative y values, okay? It's going to look very similar to the linear function that we did way at the beginning of the lesson. Okay, but instead of continuing on so that there are negative y values, it's just going to hit the x equals 0 or the y equals 0 and bounce back up. Okay, so you'll have the same values. Okay, so you're going to have the same type of graph in this quadrant, but when it hits the y equals 0, it's going to bounce back up and go into this other quadrant. Okay, so it's going to bounce and go up here. And that is your reciprocal graph. Okay, your domain is everything. There are no restrictions for your domain, so x can be everything. Your range, well, your range is y needs to be greater than or equal to 0, provided that y is an element of all real numbers. So essentially, no negative y values. Your x-intercept is going to be at x is equal to 0. That's where it crosses the x-axis. And your y-intercept will also be at y is equal to 0. That's where it crosses the y-axis. But essentially, those are the parent functions that we will be looking at throughout this unit. Okay? And make sure that you understand how the original graphs look, because what we are going to do is we are going to stretch, compress, and move them around. Okay, but those are the original functions. All right, so we call the transformations of the form y is equal to a, and then in brackets, x minus h to the power of 2 plus k. Okay, a is going to be your vertical stretch. Okay, so how are your y values going to be affected? Okay, so those are going to be affected by whatever value a is going to be. Okay, h is going to be your horizontal shift. Okay, so that's whether or not you're going to move it left or right. And k is going to be your vertical shift. Okay, so that's the notation you were using last year. This year, the notation is going to be a little bit different. Where y is equal to a, and then a times f in bracket b times x minus h, close those brackets, plus k. The main thing that we should probably highlight is that b must always be factored out. Always. Okay, so whether you're doing transformations for this unit or the other units that you're going to be doing transformations for, your b value must always be factored out. And essentially what b is, okay, b is going to be your horizontal stretch. Okay, that's what B will represent. So we have, if we just go back up for a moment, A is your vertical stretch. Okay, so how it's going to be stretched about for your Y values. Okay, your horizontal shift, so how it's going to shift left or right. Your vertical shift, how it's going to shift up or down. And now you have your horizontal stretch, so how it's going to stretch for your X values. Okay. Moving on to what a translation is. So a translation is a transformation of a graph in which every point is moved in the same direction, up, down, left, or right. Okay. Some other common terms are basically a shift. So it can be called a shift or a reflection. Okay. So we're going to do a couple examples as to how the certain reflections and shifts will work. Okay, so recall we're going to sketch y is equal to x minus 2 to the power of 2 plus 1. So the main thing we need to do first is we should be graphing the parent function. Okay, so the parent function. Okay, so the parent function is y is equal to x squared. Okay, so it'll look like this. Okay, so now that we have done that, what we're going to do is we're going to identify what a, h, and k are. Okay, so that's what we are going to identify. So for this particular graph, we're going to say a. Okay, so because there is no number visibly seen here, we're going to say that a is going to be 1. Okay, the next part we have is h. Okay, so h is going to be your shift. So h is going to be 2. And what that means is we are going to move 2 units right. Okay, so that's what that means. And then next we have k, and k is going to be 1. And what we're going to do with the k is we're going to move 1 unit up. Okay, so this parent function now, we're going to move it 2 units to the right and 1 unit up. It's going to look the exact same. There's no stretches that are being done to it. Okay, so we're just going to shift it 2 to the right and 1 up. So all these points that we have, 2 to the right and 1 up. So this is going to be my new vertex. Okay, and then your other points will be here as well. Okay, so it's going to look something like this. And this is your new function. That is y is equal to x minus 2, the power of 2 plus 1. Okay? But that is essentially how a translation will look. Okay, so when we have the graph of y is equal to f of x plus k consists of the graph of y is equal to f of x moved through a vertical translation of k units. So essentially what we have is somehow in this next graph, we have a k. Okay, so it's been shifted either up or down. So what is the effect on k? So what do we say? Okay, so we'll say if k is less than 0, then the graph will shift down. Okay, so the graph will shift down. All right, so if k is less than 0, the graph will shift down. If k is greater than 0, the graph will shift up. Okay, so it'll move up. So if k is less than 0, the graph will move down, and if k is greater than 0, the graph will move up. So you're essentially doing whatever it's telling you to do, because this is what it consists of. So if k is positive, you move it up. If k is negative, you move it down. You do exactly what it says. Okay? Whereas where we have the next one, the graph of y is equal to f of x minus h, so remember that x minus h is in brackets, consists of the graph of y is equal to f of x, moved through a horizontal translation of h units. So essentially what we're asking for is, what does h do? Okay? So you kind of have to think of it like this. If h is less than 0, the graph will shift left. So it'll move it to the left. Okay. So like an example of that is if we have y is equal to f of x minus -2. Okay, currently this -2 is less than 0. We can see that. Okay, but your graph is going to look like this. Y is equal to f of x plus 2. Okay, so even though it says it's plus 2, okay, you're still going to shift it to the left because it's actually -2, because this is y is equal to f of x minus h. Okay, So in order for this to become positive, that means our h value had to be negative, because when you have two negatives, they make a positive. Okay. For the second part then, if h is greater than 0, that means the graph will shift right. So it'll look like this. We have y is equal to f of x minus 2. So this one will just shift. So this will move 2 to the right. Whereas the one up here would move 2 to the left. Okay, so how I like to think of it is whatever the bracket set, whatever is only inside the bracket. So this refers to only being inside the bracket. So only inside the bracket. You do the opposite. Okay, so what do I mean by that? Well, in this particular example where we had, if we're just looking at this, okay, so if we're just looking at f of y is equal to f of x plus 2. This is saying plus 2, so we would automatically think that, oh, we should, that 2 is positive, meaning that we should move it 2 to the right. But because it's inside the bracket, we should do the opposite. We should actually be moving it 2 to the left because it's doing the opposite of what we want. Okay? Whereas, if we look at this one, the f of x minus 2, so this looks like that we should be moving it 2 to the left because that 2 is negative. But we should be doing the opposite because it's inside the bracket. So because it's inside the bracket, we should be moving it 2 to the right. Okay? This does not work for k. K, you do exactly what it tells you to do because it's outside the bracket. Okay? So because it is outside the bracket, you do exactly what k tells you to do. If k is positive, you move it up. If k is negative, you move it down. If it's inside the bracket, you do the opposite. Okay, so if it looks like, and I'm telling you, if it looks like f of x plus 2, right? So if there's a positive in there, move it to the left. If there's if it says there's a negative in there, you move it to the right. Okay, so it's just a way of remembering what to do when it's inside the bracket. Okay, so what I'm going to do is we'll do an example of how k and h will affect certain graphs. Okay, right, moving on to the examples where we're going to look at how k and h affect graphs. All right, so we have the first one where it says y is equal to, or sorry, y minus 4 is equal to f of x. So what we're going to do before we do anything is we are actually going to move that 4 over. So we're going to add 4 to both sides. So now we get y is equal to f of x plus 4. This plus 4 means we are going to move 4 up. Okay, so that's what we are going to do to this graph. So all these particular points that are graphed there, we're just going to move them 4 up. So now what we do is we connect the dots. And that's it. Okay, so that is this example where we move 4 units up. Again, because the 4 is outside the bracket, we do exactly what it tells us. Moving on to B. We have y is equal to f of x minus 3. So what this means is we are going to move 3 down because this is outside the bracket, so we will do exactly what it's telling us to do. So we will move 3 units down. Okay, so when we connect the dots, and that is this particular graph for moving it down 3 units, okay? So that's how, again, that's how k will affect these graphs. Moving on to the next example where we have y is equal to f of x, f, and in brackets, x minus 5. Okay, so now we're going to look at the h values and how the h values are going to affect these graphs. Now, because it says that there are this x minus 5, okay, we are going to do the opposite. Okay, so this should be telling us, okay, you should be moving it to the left because this is there's a negative sign in there. But because it's in the brackets, we are going to do the opposite. So we're going to move this graph 5 units to the right. So let's go ahead and let's do that. Okay, so each point is going to move 5 to the right. So what we're going to do is we're going to graph these points. Okay, so again, whenever it's in the bracket for h, you just do the opposite, okay? And finally, the last example, we have y is equal to f, and in brackets, x plus 4. So again, because this is saying plus 4, we are automatically thinking, okay, because it's positive, I should be moving to the right. But because it is inside the bracket, we will do the opposite. So we are actually going to move this graph 4 units to the left. Okay, we're going to do the opposite of that, okay? So let's do that. Let's pick up this graph and move it 4 units to the left. All we have left to do now is recreate the graph. We have recreated this graph, just moving it over 4 units to the left. It is the exact same graph. There have been no stretches, no compressions to this graph at all. All we've done is we've just picked up the graph and moved it 4 units to the left. Okay? So that is how h will affect these graphs. Well, that is it for today's lesson on translating graphs of functions. I hope you enjoyed it. Remember, when it comes to math, keep calm and show your work.